So I welcome you to Rosetta, your ticket to a comet. A fun fact as to why it's called Ticket to a Comet is that the Rosetta mission cost the European citizens the price of a movie ticket for the European Space Agency to build and run the mission in its entirety. So I thought that was kind of cool that it's tied to a pass for a movie. So my name is Kristie Llera, and in the theme of the movies, I'm going to start with a movie teaser. Now, if we look at this, it looks like it's snowing, right? But something doesn't quite look right. When you keep looking at it, this is not on Earth. This is actually pictures from a comet. So did you expect to see this type of rock formation and snowing effect in a comet? Well, if you didn't, the snow is not actually snow like ice. We are seeing dust, and we're also seeing in the background stars. So around the direction that I put here, you see the stars coming from the top to the bottom because the comet is rotating. And then you have more dust and solar particles coming in from this direction. And this cliff here is pretty high. It's actually bigger than the Eiffel Tower. And the images here are about 25 minutes that has been sped up into this black and white movie. And then also technically this we're used to seeing as up and then this is the ground, but there really is no up in space. We're just used to us standing on the ground and then whatever is above us is up. So this picture is actually rotated. So the up that we're used to is at the top. And then let's see, there we go. Now, throughout history, we've been looking up at the sky and also documenting what we see as soon as we start recording anything in any civilization. As we look up in the sky, we've noticed comets, and they look quite different, and they're rare over time. So if we look at this tapestry, I want you to take a moment to see if you can spot a comet, and I'll highlight it in a moment so you can maybe chat and say, I see it, or I think I see it. I'll give you a moment. This tapestry is actually from 1066 AD, and it's depicting several scenes in London, and it actually has the Halley Comet somewhere in it. So continuing, I highlighted it in the red box, and here it is a little bit bigger. So how did you do? Did you find it? And then also, how does it compare to what you think the comet should look like? Granted, this was way many years ago, so there was no cell phones, there was no cameras, not even the internet. So looking back into how soon or what's the earliest comet that we have a recording of, you have to get a little creative. You have to go and look at whatever has survived time, and you have to look through books, through art, through textiles like this one, and even songs or poetry. Shakespeare has talked about a comet, for instance. Okay, but looking at this picture, this is probably what you would think a comet would look like. This is how we see comets from the ground. And have any of you seen a comet before? You can just write it and we'll go back to it later. Well, this one is rare. This is considered a great comet, and it's one of the brightest ones that we've recently seen. It's a Hale-Bopp comet from 1997. And you can see in respect to people observing it, it was really bright in the sky. Now, this particular comet is a long period comet, so if you missed it already, we won't be alive for the next one. It will take over 2,533 years for it to appear again for us. And it's called Hale and Bopp because of the two people who discovered it, and it's Alan Hale and Thomas Bopp. Now, obviously that one in 1997, it was before our time, but the concept remains. If you look at the comet, you have what we call two tails, and sometimes even more. So what are comets? Comets are actually frozen rocks made of gases, ice, and dust. As they travel closer to the sun, you can see that the tails are getting larger, and that's because the material is sublimate. So what does that mean? It means that you have trapped gases, and as the sun heats it up, the gases go from a frozen solid state to gas. If you know nitrogen ice, nitrogen goes from an ice to a fog. It doesn't become a liquid. And that's what happens in space for these comets and these cold ices. These tails can be much longer than the actual comet. The comet would be a small rock. They can reach several million kilometers. That is much longer than the actual object in space. As the comet travels faster as it gets closer to the sun, it will also slow down as you go further. So it doesn't show the full orbit here, but you can imagine the ellipse completing. So the bigger the orbit, the longer it'll take for the full orbit to go around. And then usually sunlight is strong enough that these comets are getting brighter and bigger right about Jupiter's orbit. So if it gets closer, we'll start seeing it getting brighter. Okay, so like I said before, the 1997 was before our time, but this one was actually from last year. So the Neowise comet was passing through our skies in July of 2020. This particular image is composed or has 134 images put together to make the image more vivid. What that means is that it helps have the comet pop up from the background sky. And then the comet has a nucleus, which is the physical rock part of the comet, but then that is, you can't actually see it when we're observing it because it's hidden in this brightened cloud, which is the coma. Once again, the tail is much longer than the comet itself, and that shows how powerful our sun is. So let's break it down a little bit. So if you look here, I highlighted that inside we have the comet rock center, the nucleus, and it's about 5 kilometers, so we can't see it within this brightness, but the brightness itself is the coma. And you can see that this bright area is due to the sublimating from the sunlight that was spoken before. The word coma actually has a Latin root for hair, and this is also where that tail grows out of from the gases that build here. Those get left behind and get left in space as the comet keeps moving towards the sun. This picture is great because it has many tails. There's lots of colors between here that if you can see it well. This one has more of a violet and red, then it goes to blue, some reds here, and then the dust, which is diffuse scattering. So it's bright because it's little dust that's capturing the light from the sun. And it has a feature where the dust curves, and it's because it's slowing down as it's further away from the comet. So it has an arc to it. And what's interesting is that there's lots of sizes in the dust composing the comet. But what's interesting is that if you look for one strand of hair, there's some dust that's smaller than that. Even this, we call it the web silk, but how the spider makes their webbing, there are dust grains smaller than that. And then also the water is a strong feature for comets. And in the 1950s, that led to the theory that comets could be the source for how water got to Earth, but that doesn't necessarily mean that all comets have the same recipe for the water that we have. I'll talk about that a little bit later. But some of the colors that you can see is when you're observing, sometimes you see green. In this picture, you see some blue, some red, and yellow. And I kind of put a little description of what it is. So it's sodium ions, but that's salt. And then you have water ions, and then that shows up as blue. And then CO plus is kind of like what your car releases when you're driving. So that's not good to breathe, not CO plus. Getting closer. So most of what we know from comets are what we see when we're watching the sky from Earth. Not all comets are bright enough for us to see with our eyes in the night. So it's interesting that although there are more than 6,000 comets in our solar system, only 8 comets have been visited by the spacecraft. These space missions were quick flybys, meaning here comes the comet and we just went by it. So not much time in observations. So Rosetta is different in many ways because it will not only chase a comet, but it will follow it as it travels close to the sun and around the sun. And that's never been done before. And even at the time of its planning, no mission had even gotten close to a comet. Missions to comets started in 1985 or so. Okay, so Rosetta has a mission to catch a comet. Which comet does it choose? Well, it chose this one, and then named after two scientists that discovered it. So I probably would say it awfully, but I'll do my best. Chermanov and Sanenko. And then what's good about the comets is that although they give the full name for the people who discover it, we also have a naming convention. So what we do is that we give a number on how, in order of when we discover it. And then the P is that it's periodic. So that means this comet regularly we can know and predict in the future when it will come back near the sun. So for the rest of the talk, I'll say 67P. 67P is a short period comet, and that means that the orbit is very short. What this means is 6.5 or 6.5 years. In our case, there are comets that are thousands of years of an orbit, so there's a huge range in the orbits. What 6.5 years relates to is that this particular comet goes from about Jupiter to about just outside the sun's orbit. I mean, the Earth's orbit. It doesn't get too close to the sun. And that makes it a little more easier to get to when they were designing how to catch up to the comet. And because it's so close between Jupiter and Earth, we used Jupiter and Mars to help maneuver the spacecraft to get there in 10 years. Another good thing is that the 67P comet is not very active, so we can actually image it from the ground. And here on the right is the best model we can come up with before the Rosetta mission with just the ground observations over time. As you can see, we can't tell much, and we need an actual mission to learn more and see more. Now, another question that could come up is, why is it called Rosetta? Well, Rosetta Stone had a message written or transcribed in 3 languages that are ancient today. So old that we did not even know how to read the Egyptian hieroglyphics that were one of the languages. But by comparing the other 2 translations, scientists were able to learn the Egyptian hieroglyphs because of the other languages among the rock. So ESA, this European Space Agency, also hoped that observing a comet for a long period of time could be a Rosetta Stone for the formation of the solar system. Finding out what the comet is made of could be very complex, and that can mean a lot of things for the formation. So some of the complex molecules would be the building blocks for life on Earth. For example, what makes up proteins? That's an example of a complex molecule. A simple molecule could be water because it's hydrogen and oxygen. Rosetta could help answer whether there's water from Earth that came from comets that hit the Earth, and then also whatever we find as our close observations from it, it would help us to see if there's what was available during our solar system and what helped create these moons and planets, because the rock basically froze all those particles and stuff in that time when the formation was stopping. So they basically are little frozen ice balls from millions of years ago. Okay, so now I have a video. This is how science is inspiring the movies or science fiction. Hopefully you guys will hear it. Let me see. Okay, I'm going to start it again just in case because I'm sharing sound.
What is the key to life on Earth?
Water.
Water. For a long time, the origins of water, and indeed life on our home planet, remained an absolute mystery. So we began searching for answers beyond Earth. Where could all this water have come from? In time, we turned to comets. 1 trillion celestial balls of ice, dust, complex molecules left over from the birth of our solar system, once thought of as messengers of doom and destruction, and yet so enchanting that we were to catch one. A staggeringly ambitious plan.
Are you talking about the Rosetta Mission?
Throw me the probe. We harnessed whole planets and their gravity to chase down the comet. So many things could have gone wrong. A failure at launch, an error in the calculations, collisions.
Okay, so in that video, it kind of summed up why Rosetta was so ambitious. There was a lot of firsts that happened for this mission. I know there's a lot of words on there, but essentially, to summarize it, it caught up to the Comet 67P. It stayed close enough to study it and how it evolved for over 2 years. It even landed on the comet. That was the little Philae, the little part that was detached. And then during the journey itself, it's not enough that it wants to catch the comet. It did a lot of maneuvers and it had a lot of targets along the way. One of the targets I wanted to show is asteroids. Asteroids are a little bit different than comets. While comets are fast and filled with gas and ices, the asteroids are slow, they float on by. They also have very little to no water or ice in them. Asteroids are more localized in our solar system. Mainly, we have an asteroid belt, and that is between Mars and Jupiter. And there's 2 asteroids that Rosetta flew by, and both of them look very different. So the first one is Steins, and it's more of a diamond shape, and it has a big crater at the top. But the size itself is around 5 kilometers. Then the second one, Lutetia, is a very round but very large asteroid. It's unusually big. It is 100 kilometers in diameter, and it's on the higher end of what you would see in the asteroid belt. But even so, you would think it would be big enough to be a perfect circle, but you can see dents and bumps of other collisions affecting its shape and size. And now we have another quick video. I just want to show that ESA also did a Once Upon a Time Amazing Adventures of Rosetta and Philae, and it's a series describing all what took for the mission. So here's just a clip it's about 2 minutes on how it finally got to the comet.
The route to the comet was complicated, and she had to carry out some difficult maneuvers. She had to change her speed to match the comets, otherwise she would fly past. One false move and she might not make it. There were 10 maneuvers to complete, but Rosetta was determined. As she checked them off one by one, the comet got closer and closer. It was the most wonderful sight that Rosetta had ever seen. There was only a little way to go now, but she knew that once she got there, there would be no time for rest. She and Philae had the most important jobs of their entire lives ahead of them. Rosetta's exciting mission was to follow the comet as it traveled around the sun. She would learn all about the comet and how it changes as it gets warmer and warmer, while Philae would visit the surface. But as she got closer, Rosetta realized that the comet was much more complex than people had first thought using telescopes from far away. It almost looked like 2 comets stuck together, and from some angles its shape was really rather strange. It was the beginning of August, and Rosetta had to maneuver several times to get closer and closer to the comet. The nearer Rosetta got to the strange world, the more wonders she discovered on its surface. There were craters, cliffs, and boulders the size of houses. Rosetta spent many weeks studying the surface of the comet, sending lots of information back to Earth. She also started to analyze the dust and gas around the comet. But there was always one question in the back of her mind. Where was Philae going to land? No spacecraft had ever attempted to make a soft touchdown on a comet.
Yes, and it was very stressful, but I'm glad to report Philae did land, but it almost didn't get to land. It actually bounced 3 times before it finally stayed
Route
on
to
the
the
ground.
comet was
Okay. And thanks to Rosetta's instruments, we got to get really close to the Comet 67P. And you can see from the picture on the left, you had the best we can do from the ground when we're observing Rosetta. And then here on the right is a picture as we were approaching the comet. It's not actually the closest because at the end of the mission, we actually crashed into it as well. So we have pictures that are even more detailed than this one. But first, you can see that the shape itself and the surface is a lot different than we could have imagined. There's also a neck region. In the video, it looked like a duck at some times. And that neck feature might be more common for shapes of comets. Before we thought they were more circular in shape, but now we know that there could be an actual neck or part that's more, we say more eroded, but that means more particles come out of that area, so it's smaller. Thanks to Rosetta, we get to map out the comet and we get to monitor the changes throughout the mission, and that was over 2 years. The observations from the comet also helped us understand the data and the data from other missions, the flybys that happened before it, we were able to compare with those. And then because we were able to observe it for so long, that allowed models to be tested against the data. And there's still a lot to look over in the data for the mission that ended a few years ago. Here's some of the vital statistics from 67P. I want to note the density. So the density is, a density of 1 is water. So if it's less than that, it will float. The more this, the comet is more dust than it is ice, and it spins on its side. So you can see it imagining like this. And the duct shape is between 2 and 5 kilometers. But what does 2 and 5 kilometers really look like? Well, I put here in real scale. So in the US, the Comet 67P would be about the downtown area of Los Angeles, or it can fit inside Mount Fiji, like you would when you stand under a tent. In this picture, it's true to scale between the monuments and the comet. So you have the Statue of Liberty or the Eiffel Tower. Both of them are along the long side of the comet. And then for reference, the Eiffel Tower is 324 meters tall. And then the neck region is this part that is missing from it. And then this gap is due to the erosion. So the more materials that has escaped the comet in this area, and it's due from outbursts. And an example of outburst is here. This is how we consider the activity level of a comet. As it starts waking up and it gets close to the sun and more is sublimated, you'll see these streaks of bright beams of light. So as the dust escapes from the comet, the dust reflects the sunlight, and we can see that dust component as the bright stuff in the image. And this is the source of why such small celestial bodies can produce these big bright tails, and why these small objects can be seen as very large objects in the sky. Earth is about 1 astronomical unit away from the sun. So if you take that distance, about 3 times as far, Rosetta started to wake up and become bright and increase in activity with these outbursts. Each picture is a different occurrence, and eventually it developed a weak coma. So in the last picture, for example, you can see that it's not really black. In the rest of the picture, it's wakening up and becoming brighter. And that's showing the signs of a developed coma, meaning there's enough coming off the comet that it starts covering the comet, and that's the coma. For some science, so the scientists took the mass of the gases and the molecules found in the coma. From this graph, the mass increases in the right. So as we go here, it gets heavier and heavier to the right. And the peaks is to show the unique elements and the molecules that we can see. The stronger the peak, that just means there's more of it relative to the rest of the environment. Diatomic oxygen is the strongest peak, so it's right there at the top. And this is big. When we breathe air, it's the oxygen, the O2, that we're actually taking in into our body. So it also helps to determine the distance from the sun. How much O2 can help find out where it was when it was being formed, and then also what type of temperatures, because there's certain temperatures where these molecules can freeze. So if we see a comet with it, it can tell us, oh, it has to be at least this cold. If another comet doesn't have any, it could be because it wasn't the right temperature or it wasn't in the right distance from the sun to be captured in the comet. There's other organics also, because there's lots of peaks and colors in this plot. And some of those are indicative of building blocks for life. And things like that would be something like an amino acid. So we found actually glycine in here, and that's a really good common part that builds the proteins that are in our body. So that's big news. Okay, another highlight is the water. So there's a big debate on whether all or some comets were bombarded or they hit Earth, and that's what populated the water we see today on Earth. A good marker for the water is that depending on where you are, whether it's Jupiter, Earth, the Sun, and or any other planet. Where's my cursor? There we go. All of these are in blue. They have different ratios. So water is water, but when you take a closer look, there's a combination in the weight. So there's water and then what we call heavy water, which is deuterium, and it means that we have an extra hydrogen in that water molecule. In the plot in blue, there's a blue line horizontally, and that's the unique value for water. And then if you are at a different location or a different planet, you'll have a different ratio for water. So it's really good to see if the ratios match, they have a common origin. And it turns out that 67P is 3 times as high as the water ratio that we have on Earth. But there's other comets like the Hartley 2 that matches. So maybe a longer comet like this one could have helped produce the water on Earth, but not a comet like Rosetta. And then this is some fun to continue on online. For those that like games, there's a game called comet-quest, which helps you learn the science behind it. And then also moving on, you can actually 3D print this, so you can get a 3D object of the Rosetta. The link for that is here. And then you can also shop on the Rosetta site. And there's a teddy bear, just like the cartoon, that you can get a pillow version of that. And it has Philae as well, so you can detach it and so forth. And then that's the same location where you can finish the Once Upon a Time series. I think it's a total of 30 minutes of the full cartoons. And then the Ambition video that I showed about the science fiction also is there. Okay, let me see. And then mark your calendars for a glimpse of this. In December, you should be able to start seeing this latest comet called, oh, it's covering my screen, Leonard. It was discovered this year, actually. And as soon as December 14th, we should be able to see it right after the sun comes down, so at dusk. In the US, we can see it at 30 minutes or so, but you'll have to see how it is in your side of the hemisphere. It might shift it a couple days, or it might be a couple hours. And then, yeah, so here's a good break for questions and then seeing how we're doing in time.